Change my background.
Welcome, everyone. We are the QSC Summer School, and I'm going to turn it over to Travis to begin talking about this interactive section.
So it's actually going to be me, Nick Bronn, starting out. We decided to switch order.
You switched order. Yeah, sorry, Nick, go ahead.
All right. Hey, no problem, Claire. It's great to be here at the first inaugural summer school. We're both going to be, me and Travis are both going to be talking about different aspects of Qiskit, which is our open source platform for quantum development. There's a lot of things that go into it, including compiler visualizations, benchmarking, and a number of modules, some of which I'll be talking about with regards to nature and operator flow and pulse and the transpiler. And I believe Travis will be telling you about the optimization module. So first of all.
Oh, one moment.
Yeah, sure thing.
People to ask questions while you're going through, and I can read those out to you.
Yeah, as long as you can moderate, I think that would be great.
Okay, great. So
Perfect.
If you have questions, put it in the Q&A, everyone watching.
Okay, happy to make sure this goes. Okay, so we're going to start out with a little overview of Qiskit Pulse. What Qiskit Pulse does is it's one of the modules that allows you to do kind of lab level experiments, but anywhere over the cloud on our hardware located in New York or Germany or Japan, anywhere. And essentially it works by defining a few channels that you can do things with. So pretty much the two things you want to do to qubits are you want to control them and measure them. And we have two different control channels that we use for our qubits. We have the drive channel, which is essentially on-resonant drive, which does single qubit rotations. And then the type of two qubit interaction that IBM uses is something called cross resonance, where we drive the control qubit at the frequency of the target qubit. So that ends up being an off resonant drive on the control qubit. So that is something separate we call a control channel. These frequencies are in the microwave regime, typically around 5 gigahertz. There's some natural spread so that we can address the qubits in this cross resonance technique. And then we have measurement channels, which are done by readout resonators around 7 gigahertz. And so that would go in kind of the measurement channel. And this is typically the kind of thing is that you would have a number of control pulses and you have a measurement channel, a measurement pulse that's applied. And then along with the measurement pulse, you'd have an acquire channel, which would acquire the signal, the phase imparted on that measurement pulse that gives you the information, whether you measured a 0 or 1 state of the qubit. And so the kinds of instructions you can play on these channels are the kinds of things you would like to do. You'd like to play pulses, so you can generate any kind of pulse waveform you have, with the limits being the electronics that we offer. You can have delays between these pulses, for example. You can also do frame changes, which shifts the relative phase of the pulses, which in a way gives you a virtual Z rotation. Instead of actually doing physical pulses, we can do those in software. And then we have an acquire, which is like a trigger that will acquire the measurement pulse on the acquire channel. And then from this raw waveform data, we can integrate it against a kernel to get a point in the IQ plane we call a shot. And then from these shots, we can discriminate them as 0, 1, or even higher order levels, for example. And so just to show you kind of a picture of what I think about when I think about the pulse model is, people often think about the circuit model. So if you want to generate, say, a Bell state, for example, you do a Hadamard on qubit 0. With superconducting qubits, we always assume we're starting in the 0 state. That's the ground state. So the Hadamard will put the Q0 in a 0 plus 1 superposition. And then by applying a C naught to that, I can get the 0, 0 plus 1, 1 Bell state. And then I'd measure those, and those would be extremely correlated with each other to within the errors. Now, this is not a native gate set to what the actual superconducting hardware does. The superconducting hardware responds to microwave pulses. So that's where we get this kind of more experimental picture. Sorry. There we go. And when you schedule the pulses that come from the circuit, you actually get a series of these colorful pulses right here. And so we have all these channels that I was just talking about before. We have the drive channels of qubit 0 and qubit 1. In the blue, those are the on-resonant single qubit controls. We have the yellow, which is the off-resonant cross-resonance 2-qubit gate controls. And then we have these measurement and acquire ones right here, the measurement in red and the acquire in gray. And those are, in this example, coming after the experiments, but we have recently implemented mid-circuit measurement and reset, so now you don't necessarily have to provide your measurement and acquire statements after the control. You can come back and do more afterwards. So if you're a experimentalist like me, then you want to know what each one of these pulses is doing, what kind of interaction is it driving, what kind of rotations is it performing, and there's a lot going on under the hood here. So in particular, for example, I mentioned that we do these frame changes. These are virtual Z-gates. They change the phase of the subsequent pulses, and they take no time, so they're perfect, essentially perfect Z-gates. And they're given by these little squiggly arrows right here. Other things we might notice is that we have this derivative of the Gaussian on the quadrature of these pulses. That's because our single qubit pulses are actually not Gaussian, but something called drag pulses, which is derivative removal by adiabatic gate. So this is supposed to reduce leakage to the higher order levels of the transmon, but it turns out to get rid of other effects instead. Then we have our basic cross-resonance, echoed cross-resonance pulse, which is the typical way that we can implement a C0. The cross-resonance pulse, or the echoed cross-resonance pulse, if we were to, let me say what it does first. So first we're driving the control in the positive CR direction, and then we're flipping the state of the control. And then we are applying a negative cross-resonance pulse in the other direction. And what this has the effect of is, because the cross-resonance has two terms in it, those will add up while we'll eliminate the extra single qubit terms that come along for the ride in the Hamiltonian. And this way we kind of perfectly cancel and get only the ZX interaction that we're looking for. And by ZX interaction, I mean we take the Z tensor X Pauli matrices and we exponentiate those to generate a rotation in SU4. And what this, yep, question? Yeah, absolutely.
Yes, so people are interested in what the horizontal axis is for these.
Oh, that's a great question. The horizontal axis, so it is equivalent to time, but it's actually in the samples of the waveform generator. So our waveform generators are typically these days around 4.5 gigasamples a second. So each unit here is about 0.2 nanoseconds.
Great.
So
Thank
great
you.
question.
I'll pop up with my video when there is a question, so you can always, when you see me, you'll know. People on YouTube, you can also put questions there.
Great, thank you very much. Yeah, so what the echo does is it cancels the single qubit turns that come along for the ride in the cross resonance drive Hamiltonian. And what this actually represents is a ZX interaction. So what we do is this. We do this ZX interaction to an angle of pi/2, and that is locally equivalent to a C0. So we take that ZX interaction, we add a few single qubit gates to it, and we build a C0 out of that. So that's actually how you construct these things. And knowing these kinds of things are kind of allows you the ability to take these and manipulate them using Qiskit pulse in order to accomplish things that are harder to do with the as given native basis gate set. So continuing on, there's more stuff going on even. We have something called rotary echoes. So this rotary echoes, what this does is it rotates the target qubit at its resonant frequency. So this is a single qubit rotation of the target, and we do it and then we undo it. And what this does is it has the effect of suppressing other undesired interactions that come along, mainly from the higher order energies of the transmon. Since we're using transmon qubits, we have higher order levels that are spaced differently in frequency, so we can mostly reliably address the 0 and 1 states. But we do experience the effects from the higher order states, and the rotary echoes help us suppress undesired effects. Okay, so let's turn to quantum simulation. So when I talk about a quantum system, I think about something, in the cloud where it just behaves how it behaves, but I can describe it with a certain wave function. And I'll choose to describe that wave function by phi, and I'll say at time t equals 0, this quantum state is represented by phi of 0. And then I know by solving Schrodinger's equation that it's going to be some unitary evolution to a state phi of t at time t. So if I want to understand that system, it's very hard to go in and inspect it at different points because you're going to alter the configuration of it. So what you might want to do instead, and this is what Richard Feynman really wanted to use quantum computers for, is you want to do quantum simulation by looking at what a simulator can do. So if you have a quantum simulator, you can prepare a known quantum state, we'll call this psi, at a time 0 that you know and you make, and you can time evolve that system under a unitary evolution u prime until you eventually get a wave function psi of t, in which you can perform a measurement whenever you want to, and then you can identically prepare the system over and over again and perform measurements at different times or different evolutions. So what you can do is you can tie these two together. And so if you can map essentially your quantum system onto your quantum simulator, and then you can map it back, and then you can understand the quantum system under study by analyzing your quantum simulator. And the only real difference between these two systems is the unitary evolution which is undergone is either the unitary evolution of the system Hamiltonian or the unitary evolution of the simulated Hamiltonian. And so what I'd like to talk to you today about is how do you go between these two and then do the most efficient simulation on a quantum computer. Okay, so the first thing that we need to address is the fact that a lot of the things we want to simulate are not qubits themselves, but are actually fermions, usually electrons, for example, or combinations of electrons. So fermions obey these anti-commutator relationships that I've given you here. And for example, these could be used to describe the occupied orbitals of a molecule, which is one of the popular problems that we're using quantum computers for. And in the second quantized nature, you would get an electronic Hamiltonian consisting of on-site and hopping terms given by whether there are 2 or 3 annihilation or creation operators in there, with your coefficients here being overlap integrals between your basis sets and your molecular orbitals. So this is a common system of study, but we need to move this to a system of qubits that doesn't obey these kinds of anti-commutation relationships. So we need some sort of mapping that takes us from these anti-commutation relationships to these commutation relationships that the qubits obey. Now the qubits obey these Pauli algebra. So the Pauli I, X, Y, and Z, for example, we'll usually call these P for Pauli strings, and those are just tensor products of the Pauli matrices. So we need to map this the second quantized fermionic Hamiltonian to essentially a sum of Pauli strings with certain coefficients on it that represent the system that we wish to study. And there's a number of ways of doing this. The one that's been known for a very long time, since the 1930s, is the Jordan-Wigner decomposition. So if I write my creation and annihilation fermionic operators as this, in terms of these Pauli matrices, then I can get a explicit mapping between my fermionic Hamiltonian and a Hamiltonian that I can simulate on my system. Now, one of the interesting things here is now you have to make a decision. I have a Hamiltonian I can represent on my quantum system. I can do a number of things at this point, and it depends on which algorithm you want to run. So a lot of times this is the starting point for the variational quantum Eigensolver you may have heard of earlier today. This is where we use this mapped Hamiltonian essentially to measure the energies that are prepared by the quantum computing unit. And then you're going to essentially classically optimize over those energies in order to minimize the energy and arrive at a solution. Instead, in this talk, we're going to take this Hamiltonian and we're going to time evolve it in the system. So in that way, we're going to kind of explicitly study the time dynamics of the quantum system. Okay, so we're going to start coding here. So I'm using a Jupyter Notebook with the Rise installed so that I can kind of present this as a slideshow. But I have blocks of code that I'll kind of talk to you about and execute in front of you. So right now I'm just executing this because it takes a moment. I'm basically going to import my NumPy and my Matplotlib standard kind of libraries for plotting and mathematics. And then from Qiskit, I'm going to import IBM Q, which will allow me to load my account, Transpiler, which will allow me to convert an arbitrary circuit onto something I can run on a quantum backend, and schedule, what allows me to build the pulse schedule. Likewise, from quantum circuit, I'll import these registers that you'll see, a general parameter that I can set at the beginning and then bind to later, quantum and classical registers, and quantum circuits, of course. So what I'd like to start out with is building, let's see, I guess I didn't clear it out. I'd like to start by building building the circuits out of, or building interactions out of basic circuits. So I kind of think of the ZZ interaction as being the kind of fundamental unit, which if you look at is just, it just gives you a minus sign when you have both qubits in the one state. Now, if I actually want to see what that looks like when I put it on an actual quantum circuit, it looks like a C naught followed by a RZ rotation by an angle of theta, which would be virtual in our case, followed by another C naught. So effectively, what that would be is you'd have 2 C naughts with a different phase of the other one by an amount theta. But I can build a lot of other circuits out of this, for example. So say I want to do ZX, which is very similar to what the native C naught is. Then what I can do is actually, I have a ZZ. Well, I can just essentially, I can build on that second Z, I can put a Y dagger and a Y, or maybe a Hadamard and a Hadamard. I think they both work, and turn that ZZ into a ZX interaction. So here I have essentially the square root of x term. So this turns this into a pi over 2 rotation around y. And these signs have worked out in such a way so that they cancel each other. So that's kind of like a y and y dagger of an angle of 90 degrees. We can look at other kinds of interactions. So YY, for example, is built into Qiskit. And you can see we have a square root of x that modifies both the z and the z are modified by the square root of x gate, and then this is the inverse of square root of x gate because I've rotated and unrotated by pi. So you can do this for all kinds of things, and the basic exercise of doing this essentially is to show you for any 2-qubit poly, I can derive the circuit language for that in terms of a ZZ interaction, which I can represent with circuits. And this is kind of the final stage we want to get to from our simulation, before we run it, of course. So then we go to the transpiler, and I mentioned this earlier, but the transpiler is this very interesting system of doing a lot of things, say taking an abstract quantum circuit, by which I mean you can have Toffoli gates, you can have many qubit gates, many interactions, all kinds of systems or connectivity, and it's got to essentially break everything down into the native basis gate set of your system. It's got to break it down into the topology that you might have. If you're superconducting qubits and you're a planar technology, then you're going to be somewhat restricted. Your basis gates, for example, in our case, are going to be the square root of x gate, which has a 90-degree rotation on x, and an arbitrary z rotation and a c naught. So those are the kind of things that are given to you. And then you can optimize things further. And in fact, this is kind of an NP hard problem. So we, at our highest optimization steps, we actually make it stochastic so it runs in a reasonable amount of time. In particular, I want to talk about a new part of the transpiler called the template optimization. This is a pattern matching technique that was developed from our Zurich research lab. It's on the archive since 2019, I think. And essentially what it does is it looks for patterns in circuits by building as big of a circuit as you can, and then figuring out what the inverse is, and then asking the question whether that inverse is simpler to perform on the quantum circuit or not. Because you always have to be concerned about errors, and I'll show you that a little bit more specifically later, you want to be able to essentially transpile your circuit into something that has the most chance of success on running on the quantum hardware you have. So this is this template optimization is a pass that has been added into the Qiskit transpiler. This is kind of in addition. It's a little extracurricular from what usually happens. And in particular, me and my collaborator Daniel Egger at Zurich have come up with a way of breaking down these interaction circuits into something that has a easier pulse level implementation, and we showed that there is actually less error when you do this kind of scaling. So essentially every one of these passes is defined as either an analysis pass or a transformation pass. So in particular, this takes 2 passes. There's the template optimization pass, and what we do in there is we feed it templates that are essentially because the ZX rotation is essentially closest to the actual implementation of the cross-resonance Hamiltonian. What this does is it shows us how to take a circuit made out of C naughts that look like interactions and turn them into RZX interactions by essentially building a large circuit that is equivalent to the identity. And so the template optimization knows how to look at that and handle that and convert your circuit into something that is now abstractly consisting of ZX rotations, but then we go and do another pass, something called the RZX calibration builder. And by calibration builder, I mean we're actually going to replace the gates with a particular pulse schedule that we've optimized. And we're calling these calibrations because we're kind of allowing you to transform whatever gates we give you, or for you to build your own gates out of whatever pulse schedules you feel like calibrating. And so in this way, we can build this transformation pass that consists of ZX of theta rotations, or the actual pulse level implementation that does ZX of theta interactions, instead of just the basis C naughts that are given to you. So let me kind of show you what that's like. So I have a little demo. I'm going to import the pass manager, which is kind of manages each one of these steps, template optimization, and my builders I just mentioned. And so what I'm going to do here is look at let's say this is going to be a YX interaction, I know, because this is similar to the work we did, but I'm going to do a YX interaction to an angle of pi over 6. So I've essentially created a circuit, a quantum circuit with 2 qubits. I'm going to do a C naught, a pi over 6 rotation C naught, and I know that's a YX rotation of pi over 6. And this is implemented with 2 C0s. However, whoops. Oh, well, I already executed it. Okay. So then what I can do is I can feed that my RYX interaction through the template optimization and get a new pass and then execute it on the quantum, or I haven't executed on the quantum hardware yet, but I can generate a circuit that is the equivalent RZX interaction. So this is much closer now to something that is executable on the quantum hardware. And it's just this RZX native interaction with a single qubit rotation, one before and one after. And that's an equivalent rotation, but the difference is now the angle is occurring in the 2-qubit interaction instead of on the single qubit interaction. And this is really what I'd like to highlight. You can see the angle pi/6 here on the single qubit interaction, and here the pi/6 is on the 2-qubit interaction. And this becomes very important because the 2-qubit error rates are much higher than the single qubit error rates. Okay. So I can look at this and I can actually pass it, and what this is doing is building the is replacing that RZX with an equivalent pulse schedule, and then I can schedule these transpiled circuits. So I'm taking these circuits, although they've already somewhat been transpiled, and now I'm scheduling them, which means I'm turning them to the equivalent pulse schedule that corresponds to that. And now I have 2 different ones. I have my one consisting of C0s, and I have my one consisting of the RZX thetas. And I can just ask, and it's probably hard to see, and that probably made it worse, but you can ask the duration of these schedules, and I can see for the scaled schedule, I'm about 1150 units of the time sample DT, and for the basis C0s, I'm about 3200. So I'm about, a little over 1/3 of the time of the entire schedule of the basis C0s, the way you would go formulaically about to do these interactions if I did the scaled pulse schedule. So this is a little bit easier to see once you look at the actual pulse schedules themselves. So this is the digital one. So this consists of essentially the blue rotations. You can think of, they are single qubit rotations, and the yellow are the 2-qubit rotations. And roughly the yellow qubit, or to the degree of pi/2, each one of these is about 1% error, whereas the single qubit error is usually less than 1/10 of that. So whenever you see yellow, you kind of know you're going to be suffering from error. You also know you're going to be suffering from decoherence as you go along in time, because your qubits are always going to be relaxing and decohering. So if I just go over and I look at my scaled schedule, I get a pulse schedule which is much, much smaller, but completely mathematically equivalent to the YX of theta interaction that I wanted to perform. You can see that there's a lot of wasted time that we didn't need to use, and there's a lot less cross-resonance pulses being used here. And this was kind of the idea that Daniel and I had, because we could do more efficient pulse simulation if we were to just naively scale these pulses and show that they in fact did have less error than we would, as we would naively expect. Okay, so we applied this to a very simple braiding simulation of Majorana zero modes, which are fermionic particles that were hypothesized to be their own antiparticle. They're predicted to obey non-abelian statistics. So unlike a fermion where you get a minus sign when you change places, or a boson where you get a plus sign when you change places, this non-abelian means it depends on which way you go around when you change places. And that's kind of what I mean by braiding, is you'll go around once with each other. And so these have been predicted to arise if you have something, about 20 years ago were predicted, if you have something called a spinless P-wave superconducting Hamiltonian, which is very interesting but very difficult to find in nature, but they have been thought to be able to be engineered in proximatized nanowire systems. So you take a nanowire with a strong spin orbit coupling, and you proximatize it by putting it in contact with an S-wave superconductor. So this is something that's worked on in the lab. It's very difficult, but there's a lot of great experimental groups in the world that are working on this kind of thing. And this will essentially, the idea is we'll approximate a spinless P-wave superconductor so you can get this Hamiltonian. And so this kind of idea that came about is something called a Kitaev chain, which consists of these particles in a row, and essentially you can turn on these different kind of parameters by applying gate voltages or magnetic fields. So you have a chemical potential mu, which is how how much does it cost to add an electron? You have the hopping term T, which is what is the energy scale to jump between sites. And there's a superconducting gap parameter in here, which is not shown. But eventually, the idea is if you turn these on in the right way, you'll get Majorana zero modes that correspond to each other at the ends of this nanowire. So I'll show you a little simpler picture in the next one. But basically, the work we did was to take a very simple toy model of 3 of these wires and simulate the dynamics of braiding them around using a quantum computer and using all these techniques I was just kind of introducing. And that's what I'd like to show you today. So what we're going to use is a very simple 3-site Majorana Hamiltonian that looks like this. So we're going to start with, we're going to have these two terms. So we have these 3 wires, one on the left, one on the right, one on the bottom. And each one of those has 2 Majoranas on it. But we're only going to be explicitly looking at the occupations at the ends. So each intra-site coupling is going to be given by alpha. And so that kind of gives you the energy between those 2 Majoranas there. So this is a very simple model. So there is an amount of coupling. So these are not technically zero modes in this case. This is as simple as you can get with still doing the same thing. So that's the native or inherent intra-site coupling. And then we have these J terms, which is what we can control. And these are the inter-site coupling. So these are the 3 terms we want to control in the Hamiltonian in which to get these Majoranas to fuse on and off with each other and use that to move the Majoranas in the outside around and braid them, essentially. So basically, here's what we're going to start with. We're going to say our J01 is at its maximum value. So we've got a maximally coupled Majoranas on the input side of the left and right wires. And so we're just going to talk about what I'm labeling here as gamma 0 and gamma 1 as the Majoranas in the outside that we're going to braid around each other. And then we come up with a schedule. We have a time-dependent Hamiltonian we want to simulate. And so what we're going to do in the first step is we're going to take this J01 and we're going to send it to 0 while bringing J12 up to its maximum value. So that's step 1 here. And that effectively pulls that gamma 0 in and down. And so you've moved it from the left to the bottom. Okay, so hopefully everyone's still with me. We're going to continue doing these kinds of steps. We're going to take J12 from its maximum value and take J20 from its maximum value to 0. Sorry, from its maximum value to 0, and take J20 from 0 to its maximum value. And that will have the effect of moving the Majorana from gamma 1 from the right to the left. And then I'm going to continue this game over and over again. I'm going to let J20 go to 0 and J01 go to max. So now I'm in the original configuration I have. So this is step 3. I've gone through the 3 steps here, and so this might look like the way we started. It is, but we haven't gone all the way around yet because gamma 1's on the left now and gamma 0's on the right. So in order to get them back in the exact same configuration, we have to do it 3 more times. And now we're left in the original configuration. And then we know that if we go from the parity mapping of psi plus minus to psi minus plus, essentially we've gone from the even to odd or odd to even parity. Then we have had successful braiding. Hey, Claire, you got a question?
We do have a question. Somebody is asking, what is tau? They feel like they missed the explanation of tau.
Yeah, absolutely. So I'm sorry, tau is the time step of the braiding. So there's going to be a number of time steps that are going on here. We're going to have the braiding time step, which is given by tau, and then we're going to have something else called a Trotter time step, which is how we break tau up into smaller steps to run on the quantum computer. But great question. I should have said that out. Okay, so essentially we have this time-dependent Hamiltonian we want to change. We're going to go from 0 to 6 tau. So each braid step is just tau. But we're going to break the simulation up into time steps, and I'm going to talk about that in a moment as well. So what I'd like to highlight here is something that's very new. We've refactored Qiskit a little bit to come up with modules to address specific kinds of problems that you might be interested in solving with a quantum computer. So in particular, Qiskit Nature is there for all your kind of second quantized Hamiltonian needs. So what I'm importing here is a fermionic operator that comes from the second quantization. I'm just dealing with the second quantization parts of nature because I'm going to use the fermionic operator and build all these kinds of things. From my second quantization, I can also build mappers that will take my fermionic operator and convert it to a polyhamiltonian that I can execute on my quantum computer. And I also have the converter, so you'll kind of see how this works. But this is all kind of new. This was released in the I guess it's not the most recent. It was 0.25. It was a stable branch from a little over a month ago. So new stuff. It's really cool. So I'm going to show it to you now. Okay, so I'm going to start with the same Hamiltonian we had earlier, where we have the intra-arm coupling given by the alpha terms and the inter-arm coupling given by the j terms. And you could go ahead and just write down, because the postdoc I work with could just write this down into poly terms, but instead I want to get the software to do it and see how well it works. So what I'm going to do is write my Majorana fermions as composite fermions. Essentially, gamma x is going to be C dagger plus C, gamma y is going to be I C dagger minus C. And I can do that using this fermionic language. So I could write down gamma x is equal to a sum of my fermionic operators. And I'm using this term plus II and minus II. So plus means creation operator, minus means annihilation operator. And because I just want to deal with the 0th term, it's just a plus in the 0 space, and then II in the other one. So this is kind of a tensor product of all of them. So this means don't do anything to the other ones. For my gamma y, I can take essentially my I times A plus minus A minus or sorry, C plus, C dagger minus C. And because that's just dealing with the 0 gamma terms, I can move on to the 1 gamma terms, and now I've got the same labels, but they've got I plus I and I minus I in them as well to represent Majorana number 1, or Majorana site number 1. And then similarly for 2, I have II plus II minus. So this is kind of a common compact notation we use of strings. And then all these times we were using strings, we're actually considering tensor products of operators, but this allows us to kind of express it in a way that syntactically you can look at and understand. And because there's still some issues being worked out about the compatibility of certain concepts, I've got to look at my Hamiltonian term by term. But that's fine. So I can build my intra-Hamiltonian out of these and just essentially write down term by term what my Hamiltonian is in terms of these gamma operators that I just defined out of the fermionic operators from Qiskit nature. So then I'm going to want to map my operators to qubits. Well, I can choose a mapper, and I imported a lot of them. So I'm going to choose the Jordan-Wigner mapper because that's what we did in this work. But I could have just as easily chose the Bravyi-Kitiev or a parity mapper, I think. So we're still building all these out. There's a number of different ways to map fermions to qubits. This is just one of them. And for a 3-qubit device, maybe it doesn't matter so much. And then what I'm going to do is I'm going to add these parameters. So this is kind of why I wanted to break them up initially. Once I have these parameters, I have these elements that I can define later. And what they're going to do is they're going to exist in this Hamiltonian until I say what they are. And they're just going to be there symbolically, just like you were writing equations down yourself, which is pretty nice. And so in the end, I'll get this poly-Hamiltonian, which actually corresponds to the the qubit equivalent of my fermionic system. Oh, I said that. Okay, so then we can see what that looks like. So I can just print my poly-Hamiltonian, and you can see it's 1 times alpha times ZII plus IZI plus IIZ. Those are the alpha terms. And then I have J01 times IXY. So that's like XY on 1 or on 0, 1, and XY on 1, 2, or 2, 1, and then XYZ on all 3. So this represents like single qubit, 2 qubit, and 3 qubit terms. And you can see that it's done symbolically and it's done in LaTeX, so you can make like pretty pictures out of it. But if I was just to write it down myself in LaTeX, this is the Hamiltonian it corresponds to. And so just like I was showing earlier, there's a formula that you can go to and kind of formulaically apply this and create a circuit. And so from OpFlow, there we go. So I'm going to the next Qiskit module that I'd like to talk about called OpFlow, short for operator flow. I can write down different poly matrices, and I can do kind of Trotter evolution, and I can build circuits out of this. So what I did really quickly was I established a parameter t, and then I just exponentiated my Hamiltonian and made it my evolution operator. And then I just did a 2nd order Suzuki expansion with just 1 repetition, so you could see it easily, and then just drew what the circuit looked like if you were to have a circuit. So within just a few lines of code, I've taken my Jordan-Wigner transformed Hamiltonian and turned it into a circuit that's been trotterized however I see fit. I could change the parameters however I like, but here's a quantum circuit that does exactly what you would want it to do under this time evolution. So this can cut out a lot of work. This is a lot of stuff that the postdoc John did by hand, and now in Qiskit you can kind of do this automatically. So back to kind of a paper we did, I wanted to take a step back and look at this. So this is exactly the same Hamiltonian I was showing here. And I was just, looking at the, before the trotterization, I guess, we were looking at the, what are the actual steps that are happening? So you can see there's a y-x interaction, or sorry, there's a bunch of z rotations on all the qubits, single qubit rotations. There's a y-x interaction on 1, 0, there's a y-x interaction on 2, 1, and there's a y-z-x interaction on 0, 1, 2. Now this circuit is also executed on one of the snake devices, meaning all the qubits are in a row, which means there are no actual C naughts between 0 and 2. So we did employ a little trick to fix that. But this is essentially what your digital simulation circuit would look like. Like if you just took the formula and you applied it, you got the interactions you wanted by combining the polys in the way you wanted. This is your answer. So we've got CZs here instead of CXs. And when you're like me and you're an experimentalist, I look at that and I see a lot of C naughts, and I know that there's a lot of error corresponding to those. So our kind of average error roughly is about 1% per C naught. And these things, this particular circuit doesn't look so bad, but I know this is just something I'm going to be repeating over and over and over again as we go through the braiding evolution steps. So I'm going to take a step back and consider it. I can also look at the CZs, which consist of C naughts and single qubit gates using the old notation U2s. So these consist of a single microwave pulses. It's like a SX. And then I can look at the 2 qubits, or the C naught that's happening between 2 qubits that are not connected to each other. That means you need to have a swap between some of the qubits. So you've got to swap the quantum information in order to do that, to execute that circuit. And the swap consists of 3 C naughts. So I've got 3 additional C naughts on top of that one. So that's each of those with 1% error. This gets this gets out of hand really quickly. And the other thing is I'm going in all these like small trotter steps. In fact, I'm only going to be looking at rotations of about pi over 10 to pi over 3 in, like, say, my YX rotations. Now, when I think about these C naughts, though, I know that the way that these are built up is they're locally equivalent to a ZX rotation of pi over 2. Hey, Claire, you got a question?
We do. Mel Lynn would like to know, when you trotterize it, is there a preference which term is applied first? Does it matter or not?
That's a good question. So my understanding is it will go in order. The second order of trotterization will go in order of the terms, and will go in reverse order.
Okay.
Does it matter? That's a good question. Off the top of my head, I don't know. I wouldn't think so, but it could.
Always good to get a question that makes you think like that. Well,
right. Well, we're doing everything on our feet today, so. All right, it's a great question. I mean, these and I'd like to go ahead and say this is that a lot of these techniques are kind of empowering. So you can easily just do a bunch of different transformations, a bunch of different trotter steps, and you can compare. And this is something I'm kind of pushing people to consider is in at least the near-term noisy quantum hardware era, if you want anything to run, you need to know how to map things the best way. And this is a very important open question. And I think these the Qiskit nature and Qiskit opflow allow you to address those questions in a much more systematic way, in a way that would be very difficult if you didn't have a bunch of postdocs or something. So I hope to empower your postdocs to use Qiskit opflow and Qiskit nature to analyze these questions. Let's see. Basically, what I wanted to get back to was that we were going to do these. I'm just going to say YX interactions. These YX rotations are going to be done at an angle about pi over 10 to pi over 3. If you look at what we actually did with the number of trotter steps we chose, which was ended up being 4 trotter steps per braiding step in the actual simulation we did. And then you look at the C naughts, and I look at each C naught, and I know that that is locally equivalent to a ZX rotation of pi over 2, which means each one of these digital breakdowns of the interactions is a entanglement of pi, meaning the entanglement is essentially rotating my 2-qubit manifold by an angle of pi, which is a lot more than pi over 2 and pi over 3. So if I was smarter with the way I was using the pulses, if I was to scale them like I was showing earlier, then I bet I can squeeze out more performance. And it turns out that's what happens. So first, we're going to do a trick. I don't know how John came up with this, but he essentially came up with a unitary transform consisting of the sum of polys, which will eliminate the 3-body term. So there was a 3-body term, that YZX here. That's going to be, have to be broken down into 2-qubit terms and put onto qubits that are not necessarily attached to each other. So that was something we thought we wouldn't get rid of. And I've talked to people, and I think I understand if there's only a single 3 qubit term, you can always do this. So this will eliminate the 3-body terms and leave you with a Hamiltonian of only 2 qubit terms. So we can look at it here. I got to zoom out a little bit. But now you can see the circuit that we get after essentially just doing, we just did the math. We just reduced Hamiltonian as the UU adjoint combined with the Hamiltonian poly combined with the Hamiltonian, where I've written that, essentially I wrote the U in poly strings using the IZ X and Y from OpFlow. And just trotterized it in just the same way. And now I can see I'm much happier because I'm only doing C-naughts between adjacent qubits, which makes me sweat a little less. Okay, so in order to prepare the braiding states, we can prepare the states in psi plus or psi naught. I'm not really going to go into how this was done other than to just kind of, execute it and say it just consists of a few single qubit operations. So we can prepare the qubit in psi plus or psi minus, and then we can unwind it. And we're actually, psi plus is supposed to go to psi minus, and we actually decided to go from psi plus back to psi plus and so we just changed the way you unwind it so that psi plus to psi plus was correct and psi minus to psi minus was correct. And then I'm going to add my parameters and build my my reduced trotter circuit is going to be my operator. That is going. I'm taking my reduced trotter operator from the previous page, and that's going to be my trotter step they're going to use for everything. But I'm just going to map it to its circuit class right now. So instead of being a numerical operator, now it's going to be a circuit. And then I can perform my braiding. So so what I'm going to do is establish a quantum register of 3 qubits and a classical register of 3 qubits, and then braiding plus and braiding minus, and I just start by appending the schedule for the initialization in both the plus and the minus state. And so basically what I can do here is much simpler than what we actually did, where we actually used the pulse schedules and built them straight out of pulses. But I can go through I can go through the system of 3 steps twice. If you remember, we've got to braid 3 times to get back to the original one with the Majorana switched, and then 3 more times to the unswitched. So I just do this twice. And so each one of these steps of my 4 braiding steps is going to be essentially defining my evolution parameters for each step, and then just attaching to my braiding circuit by binding those parameters to my reduced trotter circuit that I showed you on the previous page. And so, yes, Claire.
Yes, Gideon Uchihara would like to know how can you use the trotterizer to generate the circuits for Ising models?
Oh, absolutely. So for the Ising model, you can just write down. So your Ising model is going to look something, roughly like that. Just write down your Ising model in terms of the poly operators, and then go to town. You can just here you don't need to do the transformation, but you would just time evolve your Ising model, for example, and then trotterize it. And there's different modes, different orders, different repetitions you can use, and so on and so forth. But it's just a few lines of code.
That's awesome.
Yeah, thanks for the question. So yeah, where we were, I was just going through, and this is essentially the code equivalent of the braiding schedule that I showed earlier. And what I'm going to be doing is essentially in each one of these time steps, I'm going to be reducing J01 in the first step and increasing J12. And J20 is just going to chill at 0. And then I'm going to bind those parameters to my trotterized circuit that I have and add it to the braiding schedule corresponding to whether I started in the initial state plus or minus. And so then the next braiding step you have, like the second one and the 5th one, I'm going to be going from J12 from its maximum value, J0, down to 0, and J20 is going to be increasing to J0, and so on and so forth. And you can, I can zoom out so you can see everything, but essentially it's all there, and then we unwind the qubits at the end. Okay, so get back zoomed in properly. All right, so here's let's see, I forgot to execute something, which I knew would happen. Okay, so, well, I'll just go ahead and keep talking. So I can execute my braiding circuit, and this is something where something's gotten a little tricky. So I am running it off a fork of a dev branch right here just to get this much to work, because this stuff is still under development. So it's a little just as new to you as it is to me. What I'm going to do essentially is you remember that transpiling I did, that template optimization I showed a very basic demo of in the beginning? I'm going to do that to this giant circuit. It turns out that that's a pretty greedy algorithm and it takes an extremely long time. In fact, just plotting this circuit right here already took a long time. So you can see this is just the braiding circuit plus part. So this is essentially the circuit we want to execute on just to do a single braid. So this is all 6 steps, a single braid, including initialization and unwinding. And you can see that's got a lot of C naughts. It's pretty long. It's not looking very good there. In fact, I think we calculated, we did a bunch of calculations to see what we could do. It's something like 96 C naught gates for this. So it's not too friendly there. But what we can do is this template optimization step, and well, this shouldn't have come out, but what I had done earlier is I had done this this RZX template. So what it's going to do is essentially go in and look for wherever I saw those, and of course I deleted it. Wherever I see these things that look like C naughts, RZ rotations, or RY rotations, or whatnot, the template optimizer is going to go in there and figure out how to replace that with more efficient circuits. And I want to show you what this looks like, so I'm going to rerun that code for a second. Now, what happens is this takes like up to an hour for each one of these circuits because it's such a long circuit, as I showed you before. So yeah, what it's going to do is it's going to try and build a large circuit out of structures that look like this. I've just got a C naught here, an RZ of 0.3 in this case, and another C naught. And so I know off the top of my head, that's a ZZ rotation of 0.3. So I don't need all that entanglement. I get an entanglement amount of pi from these 2 C naughts, but I only need 0.3. So I only need 1/10 of that. You can see different numbers on some of these guys, 0.06, even less, even less entanglement is needed there. So what this template optimizer is, it's going to efficiently go in there and replace that kind of circuit. The problem is it takes very long. It takes a very long time. So what I did was I output the circuits to CASM2 format, which is kind of a quantum assembly language, and then I imported it. And I'm not lying, but the RZX is not a native gate, so I had to add that to the CASM. So this is still, everything here's a little hacky when you're at the forefront of trying to do top to bottom quantum simulation, but it kind of works. We are ironing out the bugs, but this will pull out the braiding schedule that I saved. So instead of waiting an hour to generate that, you'll just have to wait 20 seconds for it to go through and draw this kind of circuit. But you'll see in the end that the transpiling step actually worked. So I wanted to show you here that now, okay, well, let me hide that for a second. Now, instead of those C naughts, you see these RZXs. So I've gone through and replaced all those C naughts with RZXs, and you'll see that the RZX rotation is an angle of 0.3 instead of pi. So you already know that you're on the right track here because you're saving yourself an amount of entanglement. In the steps, you'll actually have some C naughts around. And this is kind of the trick, is there's a lot of these single qubit gates which will combine into single qubits. So if you understand how the hardware works, like an experimentalist like me, you'll see this huge string of single qubit gates, and you'll know that that will be transpiled into something that will consist of at most 2 actual physical microwave pulses. And I think if you look at the paper we released last summer on the archive about going to quantum volume 64 using control techniques, you'll see how we did some sort of inefficient compiling of arbitrary SU4s because we can eliminate a lot of these single qubit gates by pulling them out of things. What the transpiler would do here is it would get rid of these C naughts, because if I have 2 C naughts in a row, that's equal to the identity. I know all these strings of single qubit gates is going to be at most 2 microwave pulses, 2 physical actual microwave pulses. And so I know that this can be simplified quite a bit, but I've gone through the steps that I know are going to essentially save me from my entanglement, that are going to hurt me from entanglement. And now I need the transpiler to fix these kinds of things. And it turns out that's why I was having a problem. So what I'm going to do here is I'm going to run the, I'm going to replace those RZXs with the actual pulse braiding schedule. So it's just a few lines of code to add it through another pass. And this actually runs pretty quickly because it's just substituting the RZXs with pulse schedules that we generated. And I'll kind of show you, yes, Claire.
Yes, Gideon is wondering, if you are not trading off the importance of entanglement for rotations, so between entanglement versus rotations, the importance.
Right. So the idea is, yeah, the amount of entanglement you need, like the angle of rotation is kind of the proxy I'm using for the amount of entanglement you need. They're exactly equivalent SU4 circuits. Like we have I do this all the time. We have a quantum information module. I can get out an operator class. I can put my scaled circuit in the operator. I can put the digital circuit in the operator, and I can ask if they're equivalent. And I always go through and check my work using the operator module. Sorry, the operator class from the quantum info module. So yeah, mathematically they're identical, but the implementation is way more efficient when you scale the pulses.
Thank you so much for your answer. We'll see.
No problem. And so unfortunately, what I found here, and I'll execute it anyway, is that like I showed you, so I've replaced the RZXs with my pulse schedules here, but now I need to do further transpiling to get rid of those extra, doubled up C naughts that are equal to the identity, and those the single qubit gates that will be at most 2 microwave pulses. And unfortunately, what happened is this transpiling step just undid all the work I did. So it's not quite working yet. And of course I didn't execute something. It doesn't matter, it didn't work anyway. So it turns out I only got a cost savings of I don't know what I didn't run. It doesn't matter. I only got a small cost savings because all the single qubit gates didn't go away yet. There was only a very small cost savings that doesn't really show you in this way. So what I'm going to do is just kind of show you the results from the manuscript we wrote. So skip into that. Okay, so what we actually did was we got the scaled circuit. And mind you, we got the scaled circuit because some postdoc did a lot of work, and this wasn't done with the Qiskit modules I showed you before. So in this, we essentially did something similar but almost equivalent to changing them to our RZXs. Instead, we combined all the entanglement into these atomic units of entanglement called A of theta, and that essentially consists of an echoed cross resonance. This echoed cross resonance consists of the cross resonance, a pi pulse on the control that flips that, and then a minus cross resonance, which gives you the ZX interaction if you were to flip the control back. So if I was to add another pi pulse to the control, it would be exactly equivalent to a ZX theta interaction. But here we actually did it a little simpler by looking at just the everything that was an entangler that we needed, which is the echoed cross resonance term. So these atomic units consist of these echoed cross resonance, and what we did was we scaled these cross resonance pulses. So when you think about how the hardware is turned up, is typically what we want to do is we want to make as large of an amplitude as we can without getting leakage to the incorrect states. And so we find out what that amplitude is, and we don't ever want to make it any bigger. We've made it as big as we can so that we can make our pulses as short as possible, so that we're not suffering from decoherence when we do this. So this is a common kind of calibration thing we do in the lab to bring all these. This is done with all the devices we have deployed on the cloud. What I can do is I can ask Qiskit, I can ask the back end, what is its schedule for the C naught? And I can extract the echoed cross resonance from it, and then I can scale that analytically by decreasing the width of these pulses. And so I can just get the area under the curve that I need as a relative to pi over 2, which is what I get from the backend, because I know that's a ZX pi over 2. So by scaling these, essentially I'm scaling the D, the duration, and W, the width. And then if the width goes to 0, I'm actually decreasing the amplitude of the pulse so that we can maintain a nice Gaussian profile. Or what do you call these Gaussian squares, which are essentially flat top Gaussians. Now, if I take that and I add that echo cross resonance and I add a single pi over 2 to the beginning and the end, then I actually get this circuit right here, which is a ZX of theta with a pi over 2 and a minus pi over 2 before and after on qubit 1. And it turns out this is exactly what I was showing you earlier. This is a YX interaction. So this YX up here is the digital implementation of the YX, which consists of a C naught, which is always pi over 2 of entanglement, with a single qubit rotation of theta. Single qubits, it's going to consist of 1 microwave pulse. It's going to be the same error for no matter what your theta is, and then another pi over 2 after that. However, because we're scaling the amount of cross resonance in the pulse schedule, what we're actually doing here is changing the amount of cross resonance we're doing. And so we've moved the angle into the entangler so that when we scale it down, we can reduce the amount of error. And these are both exactly SU4 YX interactions. They're just 2 different ways of doing them. And we can do quantum process tomography on them and actually analyze to see what fidelity we get. So what I'm showing in the orange is the ZX scaled. These are both YX of theta interactions, but they're implemented in two different ways. The orange is the scaled result, and the blue is the digital result. And so there was some drift over the few days in which we executed this on IBM Q Athens. And so in the blue, we get more or less a straight line as you'd expect, because we're always doing pi amount of entanglement. So you wouldn't expect things to change. Even the angle on the Y is going to be implemented by probably a single microwave pulse. So just as we'd expect, the error doesn't really change no matter what angle you do for the digital version. However, for the scaled version, you get what you would naively expect, is if you're doing less cross resonance to achieve less of an angle of entanglement, you're getting a higher fidelity. And as you're increasing that angle, that fidelity is going down and down and down and down until you're doing an amount of pi that's equal to the digital version, and they're equal to each other. So down at the end, where theta is equal to pi, you have the same amount of fidelity because you're doing the same amount of entanglement. So if you look at the relative fidelity improvement, you can see that you get a reduction in error, but around 40 to 50% around that pi over 10 to pi over 3 area of what we're doing in each one of these Trotter steps. So this is kind of the empirical proof that the scaled technique is actually working as you would naively think so as an experimentalist. And best of all, is this was just analytically scaling the techniques. We did not recalibrate anything. Recalibrations can be done, and we have a lot of work with recalibrating these C0 pulses or other pulses from these C0 pulses, but they require further calibration, which means you have to send different jobs over the cloud and receive them, and then adjust your parameters and such. Now, this is actually something that this new Qiskit runtime seeks to improve, but at the time we did this simulation, which was early November, we did not have the ability to do that. So it's very simple, and let's see. So basically, I want to just skip to the results. I was going to do some error mitigation, which comes canned in Qiskit. This is me running the step, but it doesn't work because I broke the transpiler, or the transpiler broke my circuit. So unfortunately, I can't do it live in front of you. But then I could eventually plot my data and stuff like that. But don't want to take any of Travis's time, but I think we're in good shape here. I want to skip straight to the results. So I can see that my braiding, because my pulse schedules are actually I probably should have put them in here, but they were in the paper. My pulse schedules for the scaled implementation are much less than the digital ones. In fact, it's like 60%. Like for a typical Trotter step, it's about 60% less than the actual one, and about 30% of the actual cross-resonant pulse being used. So what we did was, in order to put this in comparison, the digital simulation or the digital implementation on a quantum computer was washed out by noise. So in order to compare them, we looked at 1/6 of the braid to see how well we did. And there's some peculiarities about unwinding the circuits mid braiding, but we did our best just for comparisons. So what we show here is that the basis that you run is actually going to give you a probability of, and I should have said that, sorry, in this case, I told you psi plus was supposed to map to psi plus. So the psi plus is the successful braiding, and the psi minus is the unsuccessful braiding in this case. The high energy states, those are going to be outside the computational basis. We're going to throw those away. Those are due to the non-adiabaticity of the algorithm and due to errors that are actually run on that occur on the actual systems. So we're only going to care if we land back in the parity basis. So essentially, we want the probability of psi plus to be as maximum as possible and psi minus to be as little as possible. We see if we do the scaled noise one, that comes out to be like quite good, but the scaled even on the actual hardware was quite good as well. And so we can kind of see that we get, as we expect, the scaled performs better in braiding. And then what we did to kind of convince ourselves that the reason why it didn't work if you did the digital one was we just artificially added noise by adding time delays before and after the entanglement steps to try and figure out what the length of schedule would be when we were going to get to the digital, the same that would be for the digital schedule. And so what we can see is when we have no extra error added into we can actually get a very good contrast between braiding. So braiding the psi plus state and braiding the psi minus state. So we did both of them. And essentially we're getting a very large contrast here, which is what I wanted to plot for you. But instead, if we start adding delays, which are essentially a proxy for incoherent error, we start getting less and less contrast in braiding before it gets down to 0. And this is the area in which we expect the length of a digital braiding schedule to take as well. So this reinforces our belief that you have to be able to scale the pulses in order to achieve this result. And that's why we think this is such a cool technique. And that's why we spent the past few months putting it in a Qiskit and still hacking away at it, getting it to work from top to bottom. And that's why I'm so excited to share that with you today. So with that, I'd just like to take any other questions.
If you have any questions in either the YouTube or on the Zoom webinar, please feel free to type them. You have been listening to Nick Bronn. He's a research staff member at the Experimental Quantum Computing Center in IBM Quantum. He's been presenting on Qiskit. We have a question from Jamie Gill. Would you see any transpilation optimization by accessing higher level states?
Oh, absolutely. I am not sure that we have any of that right now, but I know, I have heard of interest in this. There have been, my colleague Nate Ernest Noble is kind of interested in this kind of thing, where you can do, you could do maybe swaps or different kind of cross resonance things by doing 2 cross resonances between the 0, 1 and 1, 2 level, for example. Now I could say it's entirely possible that it would work like from a mathematical point of view, but I should also say that being an experimentalist and having designed these transmons, the 2 level tends to be a bit noisier because the frequency is less. So like, effectively we tune the Josephson energy to charging energy ratio to be such that at our qubit frequency, there's not much charge noise. However, for transmons, that's going to be a lower frequency, like 4.7 gigahertz instead of 5, and you're going to be starting to be affected by charge noise as well. So it's definitely something worth considering and thinking about how you might do that. That's an interesting line of research. Practically, you need to be concerned about what happens with the physics as well, though.
Thank you. Do we have any other questions? I'll give you maybe another minute, but then we need to move on because next we have Travis Scholten. He's also quantum computing applications researcher for IBM Quantum. So give them another moment. There can be some delay, I know, at least to the YouTube, so. All right. Well, thank you, Nick, so much for your presentation on Qiskit, and we will move on to Travis now.
You're quite welcome. Thanks for the questions.
Yep, Travis, I'll do the same thing for you as you present. So,
sure, of course. I do have to ask, Nick, are you working from home?
Yeah, doesn't it look like it?
No, that doesn't look like it. That doesn't look like it. I'm kind of jealous of that background there. It's pretty cool. So, thank you all of you who are continuing to stay with us for the duration of this little tutorial. I know it's probably been a very, very long day and you've learned lots and lots of different kinds of things. And certainly, I'm sure what you heard from Nick was very interesting and engaging and demonstrated the kind of lower level functionalities of Qiskit, especially with respect to Qiskit Pulse and some of these sort of power user tools like the OpFlow and things like that. So we're going to kind of shift gears basically 180 degrees. And we're going to talk about tools available in Qiskit, which make it easier for people who are maybe domain experts to get up and running using quantum computing and quantum computing systems. So full disclosure, I'm not actually a domain expert in either of machine learning or optimization. I just happen to mess around with some of these modules from time to time. So in many ways, I think I'm totally well qualified to speak as to what it's like to be somebody who, I guess, admittedly, I know quantum computing, but could come into these application modules and kind of get up and running fairly straightforwardly. So what I want to do is, hopefully it'll split out roughly 50-50, though it might be more like 75-25, talking about optimization and then machine learning. And I have to preface my presentation with something that happened on Twitter when I was talking about this. So I made this post about how we're doing this virtual summer school and if there's some important things that I should relay to all of you attendees there, and shout out to Graham Smith, who's, I think he's at CU Boulder, sort of saying that it's very important, especially when we're talking about quantum algorithms that run on near-term quantum computers, to compare them to classical methods. And then, Nick chimes in here, and so Graham, if you're watching on YouTube, We have no particular reason to expect that these algorithms will perform well compared to classical computers, but it is still interesting to run them nonetheless. So there we go. I've got my complete disclosure statement out of the way. So let's go ahead and talk about optimization using Qiskit. So I'm going to actually do something slightly different than Nick. I'm going to do a little bit of hands-on keyboard sorts of things, in part because then it makes it a little bit easier for me to talk at a human pace. Shout out to Jonathan Gross from the University of New Mexico, where I did my PhD for this idea. So we're just going to go ahead and get started here. Please let me know if the screen is too hard to see. Let's go ahead and import Qiskit. We've recently had this major sort of update to Qiskit to introduce these application modules. And so therefore, it's usually a good idea to check exactly what the heck version of Qiskit you're running here. Right, so you have this Qiskit meta package, and it's got these application modules. It's got some core capabilities, so on and so forth. And importantly, we can see that I have Qiskit optimization installed. And that's what's going to provide an interface to kind of common optimization tools. In this case, something called DOCplex, which is used by people doing optimizations research and stuff like that. So what we're going to do is we're going to define a kind of an optimization problem, and then we're going to walk through the various steps necessary to actually map that problem onto a quantum computer and then simulate like running a quantum computer to solve the problem. So what we're going to do is create the model. And I have a bunch of other things that I need to import. I've selected some that it's worth bringing up here. So from Qiskit, we're going to import Qiskit simulation capability. I think we need execute to run some circuits, and we need quantum circuit as kind of a base object that describes quantum circuits. So I'll go ahead and run those things. Okay, as I said, I am not technically an applications expert in optimization, but for those of you who know about kind of common optimization problems such as like max cut, for example. So if I have a graph and I've got some nodes on the graph and they're connected by edges, what I would like to do is I'd like to partition my vertices into two groups. Yes, Claire?
Yes, Madeline would the notebook be available somewhere online?
I don't see a reason why we couldn't make it available online. It is not currently available online right now, but it's a great question. Thank you.
Okay, great. Thank you so much.
Yep. So we've got my graph and I've got my vertices, and I want to partition the vertices into two groups such that if I cut the edges that connect a vertex in one group to a vertex in the other group, the number of cut edges is maximized. Okay. So let's go ahead and do that. And maybe we're going to make a graph that has 5 nodes or something like that. And this convenience function plot graph really is to just show us that this is the graph that we're trying to do max cut over. Okay. Now there's a corresponding objective function to solve it that defines a max cut problem. It's shown here in this equation. And now what we're going to do is we're going to use something called DOCplex in order to create a model, like a model within a computer program that represents this optimization problem. So let's go ahead and say from docplex.mp.model, you can see the advantage of like commenting out the code that you're actually trying to need to type. I learned that one the hard way once. And so let's go ahead and instantiate my model. So we'll call it model, and we'll say this is a max cut. Just give it a name. You can see that we're going to then add a bunch of binary variables. So it's going to represent which group we put a given vertex in. We have an objective function. You can see that this objective function here is exactly the same as this objective function here. And we're going to define that what we're really trying to do with this model is we're going to try and maximize this objective. Okay. Now, one thing that I do really like about this module is this pretty print thing, because then you can actually take a look at what the heck model you just defined. So, okay, cool. So we can say that this is a DOCplex thing. It's got a name, right? We've got 5 binary variables, right? Because each vertex is going to be represented by a binary variable. We have our objective function. And we can see that actually our objective function doesn't have any constraints, just like, do whatever, okay? But sometimes it's more interesting to solve optimization problems where there are constraints. So let's go ahead and add at least one constraint. We'll add an equality constraint. Let's say b equals 2. And then we'll add this constraint. Oops, totally misspelled that there. Model.sum x is equal to. Oops, you can see I misspelled that, didn't I? Yeah, all right. Model constraint, and then also that. And then I totally got that wrong. It's been a long day. We'll go ahead and print that model. And you can see that now, right, we've gone ahead and added an equality constraint. Oh, actually, I can see that because I executed this cell twice, it now added that constraint once. So we've got this model defined up in DOCplex. And now we want to connect that to quantum computing. And the way that we're going to connect that is through Qiskit's optimization module. And Qiskit optimization comes with this object called a quadratic program. It's kind of a general purpose representation of a specified class of optimization problems. So Qiskit optimization import quad. Also, if my typing is super loud, please let me know. Okay, so we initialize that.
Fine.
Okay, thank you. And it's like the dangers of presenting in the 21st century, right? It's like tap, 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 tap. And okay, so let's go ahead and instantiate. Use tab completion, right? Quadratic program. So we're going to instantiate like an empty representation of that. Oh, I saw a question pop up on the Q&A there.
Yes, we do have a question. Gideon Uchihara would like to know, is the problem the same as solving QUBOs?
Is it well, you can map this problem onto a QUBO. Yes. So that's a very good question. Yeah.
Thank you so much.
Actually, I mean, you can see that even in terms of this objective function, right? That we have these pairwise products of the binary variables. So the degree of the polynomial that defines the objective function is at most quadratic. But, and this is kind of where adding this constraint is important, is right, QUBO is quadratic unconstrained binary optimization problem. What we now have is an optimization problem where there's a constraint. And so, right, great question, thank you. Promise I did not plant that one. Later on, we have some converters available inside Qiskit optimization that actually let you rewrite your optimization problem and lift the constraints. So that's great. Okay, so getting back to our quadratic program, that is a typo right there. So we instantiate it, and now what we're going to do is basically say, okay, I have this DOC-plex model up above, and I just want to ingest that thing into this object here. Okay, cool. And now we can export this thing, export as LP string, LP linear program here. And then I'm going to print this thing. Okay. And so you can see that this basically gives you the self-same information that we saw in DOC-plex. Although maybe, right, maybe it includes a little bit more information, etc. Okay. So now we can use this quadratic program object and a bunch of converters in order to map it onto a QUBO. Then later on, what we're going to need to do is map that QUBO onto an Ising Hamiltonian. And then we can solve, do something like VQE, QAOA, etc., in order to try and generate a solution. So now what we need to do is map this onto a QUBO. And what we're going to, so Qiskit ships with a bunch of different kind of converters that help you take a given quadratic program and then map it. I see a question. Oops.
Yes, Gideon's also asking for
Thank you, Gideon.
notebooks.
Cool. Oh yeah, I don't think there's a categorical reason why we can't make these available later. It's just, I should probably correct all of my spelling errors first, though.
It sounds like it'll be appreciated.
Sure. Oh, was there another? I think there's two things that showed up there.
It says not a question, so it was just a follow-up to his statement.
All right. Okay, so I think at least right now, as of this version of Qiskit optimization, we have 4 converters. So we've got the 3 listed above. I'm not going to read the names. You can see what they do. But importantly is this one, just quadratic program to QUBO, which is it packages the 3 above in a much nicer way. And you can see that what we have for our problem is we have this linear equality constraint. And so therefore what we need to do is the way that we're going to promote this or get rid of it is we're actually going to add it back to our objective function, or actually add it back to the objective function with a penalty term. And you can imagine that if we crank up that penalty super, super high, then we're able to enforce the constraint. And so you could think of this as something analogous to, if not exactly analogous to, like Lagrange multipliers, when you've studied classical dynamics and stuff like that. So let's, from Qiskit, Qiskit optimization. Hopefully this tab completes. Oh, I misspelled it. That's why it's not going to tab complete. Import quadratic program to QUBO optimization. This is not good. Qiskit optim. Oh, that's why, because I didn't use the converters. Okay, cool. So now we've got this converter object that we can use. And so what we're going to do is we're going to say that I gave this a very bad name in retrospect, but we're going to, the translated version of our quadratic program to a QUBO I'll call direct translation. Take quadratic program to cubo. We'll set the penalty to be 10. We'll play around in a moment with what it looks like if we change the penalty. And then we actually do the conversion. So it has this convert method, and that converts the quadratic program. And what we're going to get back is we're going to get back a version of that optimization problem where we don't have that constraint. I'll go ahead and print that. I'll just do this. Okay. Convert. All right. Cool. And so you can see here that now we have, again, that kind of self-same problem structure as we've been seeing all along. But you can see that the objective function has changed. And if we play around with the penalty, we'll see that the objective function definitely will change. So let's change it to 100 maybe, right? So you can see that the coefficients are changing here. And again, the reason for that is because we're taking the equality constraint, right, which was the sum of some of these binary variables needs to equal 2. And then we subtract the 2 to say, okay, the sum of the binary variables minus 2 needs to equal 0. And then we add that back into our objective function with this large penalty factor. I think we'll set it to 10 for simplicity. Okay. So now what we have, Gideon, is now we have the QUBO, right? The thing that we could map onto an Ising Hamiltonian and then use near-term quantum algorithms and actually fault-tolerant quantum algorithms to estimate the ground state F. So that was the first part of this optimization tutorial, is we define an optimization problem in DOCplex. We plugged it into Qiskit's quadratic program object in order to start manipulating and working with it. And then we use some of these converters available through Qiskit optimization in order to map it onto a QUBO. And now where we're about to go is we're going to map it onto an Ising Hamiltonian. Any questions? I mean, thank you for asking the good questions. It's really helpful. So yes, Claire.
No, there isn't anything at the moment.
Okay.
Sorry,
Okay.
it just wasn't sure if you were pausing and waiting. So
No, that's okay. So suppose that we have some QUBO. There's a pretty straightforward way to map this onto an Ising Hamiltonian, and it's to basically take each binary variable in the objective function and map it onto a qubit in a particular way. And so that's described here. Okay. Now, thankfully, this QUBO object inside Qiskit optimization has a direct to Ising method. And so we can actually just call it very simply, which is quite nice. And so what this is going to return to us is it's going to return to us the Hamiltonian. It's also going to return to us an offset. And the offset would come from, basically, you might end up with a term in the Hamiltonian, which is just a product of single qubit identities. And right, that just generates an offset vis-a-vis the coefficient of that operator. So go ahead and do that to Ising. Oops, to Ising. Okay, cool. And now we can go ahead. Let's take a look at this offset. Okay. So all this is really doing is just setting an energy scale and shifting things up and down. But the reason why it would be significant is that we have an objective function that talks about max cut, and now we've got an Ising Hamiltonian that talks about like energies of quantum states. And so we have to make sure that we keep the accounting correct as we go back and forth between those two things. We can go ahead and check out what our Hamiltonian is. Okay. And as you can see, given the substitution rule that we described, right, where we replace each, and actually I should have explained this a little bit more carefully. We replace each classical bit with, this is also another classical bit, except now it's going to take values in +1 and -1. And then we actually do like expand out the objective function. And then what we do is we look for either like these single variable z's or products of z's, and we replace those with Pauli z matrices. Okay. And so that's how we're going to do our substitution. And so because of this particular substitution rule we've used here, you can see that our Hamiltonian should only have z's, and that's basically it. And that's indeed what we have. So what's interesting, right, is we had to go through all this rigmarole because our original optimization problem had a constraint added to it. And it turns out that if we just did the naive thing of taking the DOCplex model and plugging it into Qiskit optimization's quadratic program object, and then just calling the to Ising method on that, Qiskit would say, hey, like, no, you can't do that. Okay? So we can check this out, right? And it says, boom, right? It says a constraint exists. You must get rid of the constraint, which I think is really helpful, to be totally honest. Otherwise, you might like screw something up or whatnot. Okay, so now we've taken our QUBO and we've mapped it onto an Ising Hamiltonian. And the idea of this mapping is that what we want to do is we want to prepare the ground state of this Hamiltonian. And ideally, we would prepare that ground state in such a way that if we measure that ground state and we get back a bit string, that bit string would satisfy our optimization problem with high probability. Okay? So we're going to use a couple of near-term quantum algorithms, such as the variational quantum eigensolver and the quantum approximate optimization algorithm, in order to do so. Which actually, this brings us to the third and final part of the optimization tutorial, which is actually just doing the optimization itself. Now, one of the things that you could imagine is that maybe you have many degenerate solutions. So there could be many different bit strings, which would actually satisfy this optimization problem, right? And recall, right, we're trying to partition these vertices. So there could be many different ways of assigning vertices to two different groups that all have the same value for the objective function. And so that's why we've got this code here, because what we're going to do is we're just going to take a look and ask which bit strings, which assignments of vertices to groups actually has the minimum energy. And this is just mostly a point of reference, because you would want to make sure that your near-term quantum algorithm, or any quantum algorithm that you're using to solve this problem, would actually give you a correct bit string, right? And so it would be good to just be able to enumerate what those bit strings are. And because this problem is very, very small, you can actually explicitly do that. As you can see here, colored in green are some bars that correspond to bit strings that have the minimum energy. So these would all be totally valid assignments for the vertices in our max cut problem. Now, here's where we get to something which was super subtle the first time that I tried to talk about it, to be totally honest, and it took me a little bit of time to wrap my mind around. And it's the fact that if you think about, like, what are we trying to solve? We're trying to solve a max cut problem. What are we trying to solve it with? We're trying to solve it with something like VQE or QAOA. Well, VQE and QAOA can be applied to many different kinds of problems beyond just max cut and beyond just optimization. And so therefore, the implementations of these algorithms, VQE and QAOA, are really like problem agnostic, which you would want them to be. But what this means is that there might be a disconnect between the kinds of things that are returned by these algorithms and the kinds of things that you need in order to, like, say, okay, this is the assignment of the vertices in my max cut problem. Yes, Claire. I see some questions coming in through.
Yep, they just popped up. So Gideon would like to know, is it possible to do embedding of the QUBO to the physical qubits? And then he has a second part. Also, what would you do with the QUBOs with more logical qubits than the available physical qubits?
Oh, wow. Okay. That's a very good question. So I think to answer your first question, we can harken back to something that Nick talked about circuit transpilation. Right, so we're going to have, these algorithms involve running quantum circuits, and then you have to map those quantum circuits onto hardware in order to actually run them. So I think it might be a little bit of a category mistake to say mapping a QUBO to hardware in that regard. Although I suppose there might be a category in which that makes sense. And then with respect to the second question about, well, suppose that I have a number of, I wouldn't necessarily call them logical qubits per se, right? I would say that suppose that I have a QUBO that requires more qubits than the number of qubits available on my device. What would I do? That's a really interesting question. I don't know. I suppose you'd probably want to try and find some way of partitioning the problem a little bit more, or simplifying it, or something like that. But I will note that like the opposite direction is also sort of important. Especially for like quantum annealers, right? Where like there's a lot of time is spent trying to figure out how to take the QUBO and then actually like generate these like kind of like virtual qubits by like tuning up like really, really strong couplings between the physical qubits on the chip such that they all point up or they all point down. And then like those qubits represent some like meta qubit of some kind, right? So that's a very good question, Gideon. Thank you for that. It's enjoyable.
Thank you.
So again, right, where we are right now is we're saying, well, we're trying to solve this max cut problem, but we're using these near-term quantum algorithms that are kind of general purpose in a way. And so therefore, this is why I'm going to highlight this thing, right? We have to wrap these algorithms using this minimum eigenoptimizer object. And this is going to be an object that provides a translation from kind of the results that we get from running VQE or QAOA to the optimization problem that we were trying to solve in the first place. Okay. And so this minimum eigen optimizer ships with Qiskit optimization. So we'll go from Qiskit optimization .algorithms, import minimum eigen optimizer. Okay. Then we could also, again, because this problem is sufficiently small, right? We could use a purely classical approach to doing this. So we'll go from Qiskit.algorithms, but actually this one ships from Qiskit itself, numpy minimum eigensolver. Okay. Now we get to one import, which I think is somewhat more of a historical artifact, and I think we're working on figuring out what to do about this. This quantum instance thing. It's kind of a way of encapsulating the notion of talking to a backend, or even a simulator for that matter. And then we're also going to need some backend to run this on. As I said, we're going to use just a simulator backend that ships locally with Qiskit. Simulator. I will say that the state vector simulator that I'm using, right, it calculates the amplitudes of the wave function exactly. There's another simulator, our chasm simulator, which actually can mock up things like finite sampling noise, and it can also incorporate a description of the noise that affects a backend. So it's good if you want to do noisy simulation to use that chasm simulator. If you're kind of doing this quick and dirty thing like we're doing here, and you kind of want exact results, then you want to use the state vector simulator. So we'll go ahead and run that. All right. So as I said, what we have to do is we have to actually wrap these eigensolver objects. So we'll say, all right, we'll instantiate the exact object is an instantiation of that eigensolver. And then we have to wrap it using the minimum eigenoptimizer object. Okay. Now, the beauty of this is that now this object knows that it is using this numpy optimizer to try and minimize the energy. And what I can do is I can just pass in, I use the solve method and then pass in the cubo that I'm trying to solve, and I just solve it. So we see, okay, cool. So the exact solution classically is saying that we got this optimal objective function value of 5, and that it makes sense to assign, in this case, it's going to be vertex 0 and vertex 3 to group 1, and then to assign the remaining vertices to group 2. And status equals success. I assume that's something about making sure that the optimization converged and whatnot. So, okay, cool. So we have a reference solution classically, and that's a good thing. So now let's go ahead and maybe use something like the variational quantum eigensolver algorithm. You may have heard about this yesterday or today, right? It was originally introduced in the context of quantum chemistry, but there's nothing that says you can't use it for something like quantum optimization as well. So now we need a few more imports in order to make this work. So algorithms import, right? So we're going to import VQB itself. We need an optimizer, right, in order to optimize the parameters of the wave function. So we'll get that. Optimizer. Use Kobola. And then we need an ansatz, right? That's going to be this thing here. This psi of theta is described by an ansatz. Now, what's really cool about Qiskit is that we introduced, I don't even remember how many releases ago it was, this notion of a circuit library, which is supposed to be a collection of quantum circuits that are useful in different application areas or algorithms, even fault tolerant things. I think we've got like, quantum arithmetic or something like that you can do there. But we could use, and some of those circuits in the circuit library are parametrized circuits, which means that we can use them as ansatz in things like VQB. So we're going to go ahead and import one there. Qiskit.circuit.library import real amplitudes. Okay, cool. So now that we've got that, we can go ahead and set up our ansatz. So we'll say it's real amplitudes, right? We need 5 qubits. And this ansatz, right, there's the notion of a template, like kind of a basic structure of the ansatz that you can then repeat some number of times. We're just going to repeat it once, perhaps equals 1. Okay. And then we're going to draw. And usually I like to do my output as a matplotlib, but I realize that I don't actually have that that thing installed here in the local environment that I'm running this in. So we're just going to go ahead and use the ASCII drawer. Okay. As you can see that this ansatz, right, it acts on 5 qubits. So we've got 5 horizontal wires here. And it's got some RY rotations on all of the individual qubits, and then a bunch of entangling gates, followed by a layer of RY rotations. And so what our classical optimizer is going to have to do is try and optimize the parameters of this ansatz in order to prepare a trial state which has the minimum energy. And then we're going to go ahead and configure our optimizer. Now here I'm being a little bit sloppy and I'm not going to type all of this out, but I do want to point out that, right, the function call here is saying, well, we need an optimizer. We need an ansatz. This quantum instance is going to be our simulator backend. And then we'll just seed the ansatz, some initial parameter values as given here. Okay. And you might be curious, you want to draw this. So you'll notice that this, right, VQE is the algorithm, but then because we passed in the ansatz now, this ansatz method is available to us. And so we can draw that too. And that's pretty cool. Okay. So now we've gone ahead and we've set up our problem by saying, well, we want to now solve this Ising-Hamiltonian using VQE, using this real amplitudes ansatz. And now what's really cool is we can, let's say VQE, I'll call this VQE alg. We just take our minimum eigen optimizer thing and we just plug VQE into it. And then we get a result, right? VQE alg.solve, direct translation. Oh. VQE alg, oh, oops, I missed typo there. Okay, cool. And now we're going to go ahead and inspect this result. Okay, cool. So this also worked. I mean, it's only 5 qubits. That's an encouraging thing. All right. But right, what's important here is that, well, even though, right, we've converged our optimizer and said, okay, these are the right parameter values to use to minimize the energy of this Hamiltonian, that's no guarantee that if we actually prepared that state on a quantum computer and measured it, we would always get a bit string which provided a satisfying assignment. And so therefore, then as a sanity check here, what we're going to do is we're going to go back to this VQE result and we're going to pull out the corresponding eigenstate that we've actually like converged to and look at the probabilities of getting different bit strings. And so you can see here that actually in this run, which I don't know, maybe this is embarrassing to do on YouTube. I don't know, right? But if we look at all the bit strings and we say, okay, this is a good bit string, you can see that actually a lot of the time we get bit strings which are not good, right? And so I bring this, I wanted to make sure that this happened in this tutorial to say that like, this is not, and this actually goes to Graham's point, right? This is not like a magic salve that's going to make this all so much better, right? There's a lot of thoughtful research that can go in and has gone into like what is necessary to make, VQE better for these sorts of approaches, so on and so forth. And even in kind of a problem that you might be tackling, you might need to kind of futz around a little bit, explore some, like maybe we initialized it at the wrong point. Maybe we've got the wrong optimizer, right? There's a whole bunch of work going on at Los Alamos and stuff like that about like, this whole barren plateau phenomenon and your optimization landscape not changing that much. So in that sense, right, you could look at this and you could say, well, this is bad. Or you could look at this and say, well, it's exceeded in some ways, and that's encouraging. And that's how I'm going to choose to look at it, because I can. Now we're going to try a different approach, which is the quantum approximate optimization algorithm. Right? And this was introduced back in, it's like 2014 or something like that. So I'm going to, in the interest of just, yes, Claire.
You have a question from Gideon before you move on.
Mm-hmm.
He is wondering if the quizkit.circuit.libraries also has RBM ansatz and how you can use this optimization to train the RBM circuit.
That's a good question. I don't really want to pull up the documentation right here on the fly, but I will say that we do document which circuits are in the library. I'm not exactly sure if that particular circuit is available.
Okay.
Of course, I can also then turn this back around on you, Gideon, and say, well, I mean, like Qiskit is an open source project. If you think that's an important circuit to contribute to the library, right, by all means, go ahead and code that sucker out, right? Which is actually one of the beauties of open sourcing this thing. Now, I did want to get to the machine learning thing because I think I have a personal interest in that. You're back again, Claire. You're on mute.
Gideon followed up by saying thank you. So
cool. You're welcome, Gideon. Right, so one of the differences between VQE and QAOA is the fact that QAOA typically uses an ansatz whose structure is determined by the Hamiltonian whose energy you're trying to minimize. Right, and so you can see here that when I'm calling QAOA and setting up my QAOA problem, right, there's no real notion here, at least in the way that we've coded it up here, like setting an ansatz, right? Because the ansatz is actually determined by the problem itself. And so all I can do is I can just say, okay, I want to use QAOA to solve this. And again, right, I wrap my QAOA algorithm in this minimum eigenoptimizer object, and then I can go ahead and just directly solve it. We'll get my QAOA result. Okay, cool. So, right, they all succeeded, which is encouraging and nice. But again, this problem is fairly simple. Now, one thing that you may want to know is like, well, like what exactly was the ansatz that was used given the problem that I put into it? And after some messing around, I realized that you can actually pull back an ansatz and get one out. So if you are interested in looking at the ansatz, then there's a way of getting it. And again, it would be good to make sure that, do we actually get bit strings which provide satisfying assignments with higher probability? I guess, but you can also see that this histogram is pretty uniform. So it's kind of like random guessing. So, take that for what it's worth. Okay, so in the first half here, what we've done is walk through Qiskit optimization. We talked about how you can use DOCplex to say instantiate an optimization problem. You can then ingest that inside Qiskit optimization using our quadratic program object. We discussed how you can convert quadratic programs to QUBOs using converters available through Qiskit optimization. We discussed mapping those QUBOs to Ising Hamiltonians. And then we discussed a couple of algorithms for trying to find the ground state of those Hamiltonians using VQE and QAOA. I will say that what I didn't talk about here is the fact that you don't actually have to know DOCplex. I think a lot of the functionality available in DOCplex is actually available directly through that quadratic program object itself. So if you, like me, don't really know much about DOCplex, right, don't worry, right? It's okay in that regard. So are there any final questions before we pivot and talk about quantum machine learning? I'll scroll back up to the top to buy some time. Okay, that's fine.
More
All right,
requests for the materials.
Oh my gosh, you guys, yes, we can make notebooks available. Don't worry, right? Like digital storage is pretty cheap these days, right? I remember back in high school when having a USB flash drive was considered like the epitome of tech coolness and stuff like that. And and now all the kids these days, they're using something else.
Yes, we have a question.
Yes.
Is there any implementation for image classification using QML? And that's from Shadab Hussan.
Okay, well, thank you for that question. May I flip to the tab first? Okay. So that's an interesting question. I think there's many ways of answering it. I think the short answer is yes. Quantum machine learning sounds like you've taken two of the most popular buzzwords in modern history and smashed them together. And that can be a little bit scary. But one thing that I've come to appreciate, especially since I joined IBM Quantum, which was like 2.5 years ago or something of that sort, that there is a lot of thoughtful research about how quantum computers can enhance machine learning. It's still a little unclear, I think, as to exactly, like super exactly, right, the application areas where quantum computers could provide an advantage. But for example, like one of the things that we'll talk about here is how you can basically create quantum neural networks by connecting Qiskit to PyTorch. And you can use PyTorch to tackle MNIST. And so therefore, right, like Boom, right, or FashionNet, or any of those kinds of common AI data sets. So, I don't think there's anything in principle which would prevent us from investigating that. Okay, so now we're gonna pivot to QML. So there's two things that I want to talk about here, both of which involve utilizing quantum circuits and quantum computers to kind of enhance and turbocharge classical machine learning workflows. So the first is this quantum kernel estimation, which is the way of using a quantum computer to provide a similarity measure between pieces of classical data that you could then use in something like a classical support vector machine. And then, as I just said in my answer to that question, the second part is going to focus on how we can actually connect quantum circuits to neural networks, and so therefore define kind of a quantum neural network thing using a connection to PyTorch that we've made available as part of Qiskit machine learning. So again, we're going to go ahead and do some imports, and actually, for simplicity's sake, just check that out. Oh my gosh, I really hope that these things don't crash. Okay, good. Okay. Actually, all of these imports are basically the same. There's a couple of differences for reasons that are still a little opaque to me when I was writing this. This basic error is a quantum simulation capability that ships like super natively with Qiskit, and there's not really a lot of advanced functionality available to it. Go ahead and do that. I'm going to make some plots. I'm going to grab a backend. Okay. So, to be honest, I didn't really have a background in quantum machine learning before I came to IBM Quantum, and then I've had the chance to pick up a couple of research projects involving it. And The thing that we're talking about here is the fact that many classical machine learning algorithms support vector machines, regressors, etc. Say that you maybe support vector machine for concreteness, is the decision rule that such an algorithm learns often involves a kernel. And so that's represented here in this equation where I'm saying y, my decision rule for a given data point x sub l, is going to depend upon my other data points x sub j. And the way that it's going to depend upon them is going to enter through this function k x sub j x sub l. And this is what we call the kernel. It's a way of measuring, well, how similar are x sub j and x sub l? And you could imagine, like, this sort of makes intuitively sense that, well, okay, if these two data points are very, very similar, then I should probably assign them the same label, right? Now, there's a couple of different ways that we could define a similarity measure using a quantum computer. And so what I'm showing here down below is one particular way of defining it. And so what this is saying is we're going to essentially do a Gedanken experiment of, I'm going to prepare two quantum states. I'm going to prepare a quantum state that depends upon x sub l, and I'm going to prepare a quantum state that depends upon x sub j, and I'm going to measure the fidelity of those two states. Okay. Now, there's a couple of different ways that you could measure this fidelity, right? One is to actually just run this circuit itself. The other is to use something called a swap test. What I'm coding up below is going to be the former. So that is, it's going to be a circuit who has kind of a forward action defined by u of x sub l, and then the next part of the action is the u dagger of x sub j. Now, there's a lot of interesting work that would go into, okay, well, like, how exactly do you encode classical data into quantum states? And, well, the word quantum feature map gets used to describe that. And so there's a couple of feature maps that actually ship natively with Qiskit circuit library. And so we're going to go ahead and grab one. Library. In fact, this feature map, I believe, was the basis for some work that we did a few years ago that got published in Nature. So we need a feature map because we got to encode classical data into quantum states. And then we have this object available through Qiskit machine learning called the quantum kernel, which makes it easy to plug similarity measures defined using quantum circuits into classical machine learning workflows. What I will not be showing here is actually like integrating this with scikit-learn. There are some documentation examples which show how to do that. My intention here is to provide some intuition and understanding for what the basic learning Qiskit machine, what the basic pieces are. I feel this is about to throw an error. Oh, kernels, there we go. Okay. And again, we need this quantum instance object. Quantum instance. Oh, oops. Sorry, from Qiskit import quantum instance. Oh gosh, let me take a second and then go back to here. All right, and this is maybe the slight danger of actually defining these things on the fly. Instance, Qiskit.utils, okay. Utils. But it also goes to show you, right? Like, I'm human too, right? We all make mistakes. It's okay, right? Okay, so we've gone ahead and set up some basic imports. Now, what we're going to do is in our little experiment is we'll assume that our data set that we're working with is like a very simple one. Maybe it has a feature space dimension of 3. So that is, there's like 3 features, you know. So I always use credit scoring as the example here of like, actually, I mean, I'm trying to buy a house. So if I'm trying to apply for a mortgage, right, they might say, okay, like, you know, how old are you? What's your income? You know, something else, something else, something else. And then in classical machine learning, that information is called a feature. So we're just going to assume that our feature space has 3 dimensions. Okay. And then what we're going to do is we're going to instantiate this feature map itself. And this is kind of fun. This is actually a very fun thing to play around with. So we're going to take a little bit of a moment. Okay. So this is a particular like feature map, right? You can see that it's got some single qubit gates and then it's got some 2 qubit gates. Okay. And what's kind of cool, then what I really like about the circuit library, to be totally honest, is the fact that you can kind of like very easily change the structure of the circuit just by changing a few keywords. So as I said, right, when we think about these parameterized circuits, there's the notion of a template, and then you repeat the template some number of times. And so maybe let's repeat it like twice. And so I can see, aha, I've repeated it twice. Or you could change like, how do you want the qubits to be entangled with one another? Actually make that a little bit simpler. So for example, here, you know, changing this keyword has changed like how many 2 qubit gates do I have, so on and so forth. And as you heard about from Nick's part of the talk, like the number of 2 qubit gates is super, super important. with respect to whether or not your algorithm or circuit is even going to run with high probability or low error. Okay. So now we've got a feature map. And now what we're going to do is understand how this quantum kernel object works. And the way that we're going to do that is we're going to give it two pieces of data, and we're going to say, what is the similarity measure between these two pieces of data? So we're going to go ahead and generate that data. I don't know. The low and the high here is just sort of somewhat arbitrary in a way. I just picked them because why not? Okay. And now what's really cool here is, well, okay, suppose that I wanted to compute my quantum kernel with that feature map on this data set. Like, how do I do it? Well, all I need to do is use the quantum kernel object with my feature map, or I guess instantiate this, right, with my feature map. And then also, am I going to run this on a simulator? Am I going to run this on real hardware, so on and so forth? And then we actually just evaluate it. So it's like, all right, evaluate. Okay. And so what this is saying is the similarity between these two pieces of data is 0.1. Yes, Claire.
We have a question from Mal Lin. He's not sure if he missed it, but what is the P gate?
Oh my gosh. I think that's a phase gate. I really hope I'm right on that. I think so. But that's actually a really good catch on my part that I should have taken a look at that. So thank you for that question.
Thank you.
Yep. Okay, so in these small number of lines of code, I showed you how to construct the feature map, generate some data, and then evaluate the quantum kernel. But what I would like to do in the next cell block is kind of show you the ideas behind what this quantum kernel object is using in order to do that. And so we're actually going to build the circuit ourselves. So in that case, right, we need our quantum circuit object. Our quantum circuit is going to act on 3 qubits because our feature space has 3 dimensions, and our feature map is kind of using 1 qubit per feature. I need the parameters of the feature map, because what I'm going to do is I'm going to take my parameterized circuit and I'm going to replace the parameter values with actual numerical values, and we call that binding the parameters to the circuit. So the first part that I need to do is I need to bind the parameters of my data point X to the forward action of my feature map. And then I need to bind the parameters of Y to the action of that feature map, but then do the inverse. And so you can see here, I said forward circuit, right? Just bind the parameters. But then with the inverse circuit, I bind the parameters and then do the inverse, okay? And then what I can do is I can compose, right? So notice I now have 3 circuits here, right? I've got my kind of QC, which is like the abstract quantum circuit object. I've got the forward circuit and I've got the inverse circuit. And now I'm going to bind these, I'm going to compose these together in order to create the circuit that will actually run. Okay. So first we compose the forward action. I'm going to throw a barrier here just so that way we can actually see these 2 pieces. And then we compose the inverse action. Okay, that's cool. And so now we can go ahead and draw that thing. Okay. And so you can see here, okay, right, there's the barrier, which means that all of this is the forward action. And then all of this, oops, I totally grabbed that thing wrong. All of this is the inverse action. Now we can go ahead and just directly simulate this thing using Qiskit simulation capabilities. So I'm going to instantiate a backend. I think this particular thing that I'm doing here in line 6 is going to be deprecated or is in the process of being deprecated. So we'll have to watch out for that. But essentially what I'm doing is I'm transpiling this circuit to the backend. So that is, I'm saying, okay, my circuit has these gates, maybe my backend, my simulator, it sort of speaks natively these other gates. So I got to do some gate rewriting. And then what this assemble thing is doing is it's just sort of packaging up that circuit in something that we call a quantum object. And then in order to get a result, I just take my backend and I run that quantum object. So, okay, cool. So that ran successfully. So this kernel matrix entry is simply the probability that we obtain the all 0 bit string after we run this forward action, inverse action. And so what I can do, and actually I will answer this question after executing this, what I can do is then I can just count, well, what is the, what is the number of counts that I get for the all 0 bit string? Because I'm using the state vector simulator, what this returns is the exact probabilities. And you can see indeed that this number here and that number there are the same. So we succeeded. All right, question time.
Okay, Gideon would like to know what happens if you have more than 2 data sets.
Oh, okay. So actually, this is pretty straightforward. I'll mock it up this way, right? So I have two pieces of data, right? It's not like I have two different data sets, right? Because that's unless you're doing something like transfer learning or maybe something like that, then it probably doesn't make sense to talk about two different data sets. But we can actually change here. Let's say I have 4 pieces of data, right? So instead of originally I said, okay, I have one NumPy array, I have another NumPy array. Now I'm saying I have 2 NumPy arrays, 2 NumPy arrays. Okay, so we'll just generate some more data. And now what you can see is that my kernel now has 4 entries, right? Because I have, x1, x2, y1, y2, and so therefore I need 4 entries. I hope that answers your question there, Gideon. So what I kind of appreciate about this quantum kernel object is that it would make it really easy to, for example, ingest a very, very large data set and do these pairwise products. And maybe there's probably some optimizations going on behind the scenes where maybe my naive way of calculating this kernel matrix entry is not the most efficient. So, okay. So we talked a little bit about quantum kernel estimation, and in the remaining 10 minutes or so, we're going to talk about quantum neural networks. Again, I am still very much a novice in quantum machine learning, and so therefore I will try to be precise and not say something that's too ridiculous. Maybe one thing, in order to do this, you actually need to have PyTorch installed on your computer as well. And so if you want to do that, then you can just do pip install Qiskit machine learning with this torch command as well. Now, I had never actually used PyTorch until like 2.5 months ago when I was doing a project with a Qiskit advocate. And we're looking at this from a mentorship program. And it's kind of cool. And it's really interesting to learn and grow in that way. But I will not claim to be even a Torch beginner, right? I'm like Torch kindergartner is what I am these days. So please don't ask me any really, really hard questions about Torch. The significance and where it relates to Qiskit is actually right here, this magic. Is this torch connector is going to provide us with a way of taking quantum circuits and turning them and their outputs into objects that PyTorch knows how to work with. And so again, this is part of these Qiskit application modules are trying to make Qiskit more accessible to domain end users who don't necessarily know all that much about quantum computing. So we'll go ahead and do those inputs. I'm going to just execute this cell to say we're going to generate some data. So we've got some blue dots, we've got some green dots. You can see that these dots are kind of separable. Okay. And now what we're going to go ahead is set up a quantum neural network. Now, I don't know, what's the right way of saying this? In the way that we are coding it up here, our quantum neural network consists of a feature map. Again, so an embedding of classical data into quantum state space, followed by a parameterized quantum circuit that acts as the classifier. And what the torch connector allows us to do is it allows us to take the output bit strings from running that circuit, post-process them in some way, convert that into a kind of a loss that Torch knows how to deal with, and then the Torch optimizers are going to propose new parameters that go into that parameterized quantum circuit part of the object. And so for this, we're going to import the ZZ feature map as our embedding piece of the circuit, and we'll go back to this real amplitudes circuit as the classifier part of the circuit. And so if we go ahead and set this up, right? So my feature map is going to be the ZZ feature map acting on, I guess 2 inputs. Oh yeah, I guess right here, right? My data set, it only has two features, right? It's 2-dimensional. Okay. Right, my ansatz, same number of inputs, maybe some, this linear entanglement structure. And then the way that we're going to compose this QNN or build this QNN is, again, we create a basic quantum circuit. We then compose the feature map, because you got to first do the embedding of the classical data. Again, we'll throw up a barrier just to highlight the difference between these 2 pieces. And then we'll add that parameterized ansatz as the classifier part of the circuit. And we'll go ahead and draw it, okay? And so you can see here, okay, we got the ZZ feature map to do the embedding. And then we've got this real amplitudes circuit to do the classification. Now, again, right, we run the circuit on the quantum computer, and what we get back is bit strings. And so therefore we kind of need to provide some way of mapping from bit strings to data labels. I will admit I totally just cribbed this example notebook from the documentation. And so this is the particular function that they ended up choosing to use. You can see that what this does is it evaluates the parity of the bit string representation of a number. So the number of ones modulo 2. And so you can see here that the mapping from integers to this outcome label. So what we've gone ahead and done is we've set up our circuit for our quantum neural network. We've gone ahead and defined a function which allows us to interpret our bit strings as additional input to go back into the our PyTorch connector. And so now what we can do is we go ahead and we actually set up the QNN. Right, our output data is either like, it has two values. It's either like data point, data point type 1, data point type 2. And then we use this circuit QNN object to like create the whole thing. Right, so it depends upon our quantum circuit. Right, we need to expose, well, like what are the parameters that we need to change as we talk about changing the input data. What are the parameters that we need to update using our optimizer? Right, how should we interpret the bit strings? And again, we need a quantum instance. Like, are we going to run this on a simulator? Are we going to run this on hardware? And then we need some torch pieces. And then, right, this model, this is kind of the magic of the torch connector right here, is now we take this QNN and we turn it into a model. And by doing so, oh gosh, I think I forgot to do an import. Circuit, machine learning, import circuit. Oh dear. Nope. Okay, I am sorry. I need to do a quick. Actually, in the interest of time, it might not be a good idea to run overtime, so I'm not going to do that. But it's clear that I forgot to do an import here for the circuit QNN object. But once I do that, then I can connect my quantum neural network to a PyTorch model. And actually, it's kind of good that we stopped here, because then what we get into is a bunch of code that's relevant for PyTorch. So again, the idea here is to make quantum neural networks accessible to people, developers using PyTorch. And so all of this code here, this is actually just classical machine learning using PyTorch, right? There's absolutely nothing quantum mechanical about it, right? And so therefore, if you were a domain expert, again, right, I'm like PyTorch kindergartner, you would understand a little bit better about things like, oh, well, I can change these parameters, I can influence this, I can use this optimizer, so on and so forth. But the important thing is by running this cell, then we are able to train that quantum neural network using PyTorch no differently than a PyTorch developer would train a classical neural network. And then you can do things like evaluating the accuracy of the model, so on and so forth. So actually, I'm really, really glad that we got that error. I know that this is somewhere in Qiskit machine learning. I don't remember the exact signature for calling it. So we have a little bit of time. I know it's been a very, very long day, for you all. And so thank you to those of you who are still listening. Thank you to those of you on YouTube. Graham, I'm going to be tweeting at you with the link to that timestamp where I said the thing you wanted me to say. Are there any other questions here about the Qiskit machine learning module?
I know there's a little bit of a delay, so we'll wait. Oh, sure. You have a couple of minutes left, so hopefully there's some more questions.
No, that's fine.
From Pi, we have a question. Thank you for a nice talk. This means the QML is in Qiskit is treated as a layer for PyTorch?
I don't fully, I'm going to.
The QML in Qiskit, is it treated as a layer for PyTorch?
Oh, not exactly. That we think about, right? We've got the notion of Qiskit, which is for quantum computing. And then we have these application modules, which make Qiskit more accessible for different kinds of users. And so with the Qiskit machine learning, there's a couple of different ways that we've made it more accessible. So one was this quantum kernel estimator. So we provide this quantum kernel object, but then also through this torch connector object, what that lets somebody who is a PyTorch developer do is treat quantum neural networks no differently in their workflows than they would treat classical neural networks. And so maybe like a more refined answer to your question is there's a small part of Qiskit machine learning is meant to be the interface point for PyTorch itself.
Well, thank you for that. We have another question from Quiding Andy. How is the quantum way of defining the kernel better, or potentially could be better, than the classical one?
That is the million-dollar question. So I think that there's a couple of ways that I've told people about this. So the first is you could imagine that the circuits that are used to define the feature map that go into calculating the kernel could have some property which renders them classically unsimulatable, right? That's sort of like a very standard answer. But we also know that there could be methods for like approximating the outcomes of circuits, so on and so forth, that maybe you could get, really, really accurate, but not so accurate. I will give a shout out to a teammate of mine, Jen Glick, I think also another teammate of mine, where they said, well, like maybe what you could do is you could use a feature map that's hard to simulate classically, and then you kind of do some modifications to that feature map in response to the data that you're trying to build the kernel for, and actually in order to get more like optimal classification accuracy. And this is something that's called kernel alignment in the classical machine learning literature. So there's a couple of ways of trying to think about where quantum kernels could provide a quantum advantage in that regard.
All right. We have one more question from Gideon Uchihara. What's the maximum features you can use for the current NIQ? For example, MNIST has more than 700 features.
Because I will reinterpret your question as asking our ability to encode classical data into quantum state space through feature maps. Really good question, right? Like this naive mapping of one feature equals one qubit can very rapidly become untractable, right? So it would be nice to think about other ways, like other kinds of quantum feature maps where maybe they have some provable advantage and where they maybe generate like, commercial quantum advantage, and where the number of like features that they, data sets whose features that they can encode it is, much larger. Right? That's one thing. But there's also another way of approaching it that I've seen some research papers on this in the literature of like, doing like PCA and basically just saying, all right, we got to like crank on this and reduce the number of features until it becomes something that's super, super manageable. So I think by attacking the problem at both sides, right, maybe there needs to be some novel research in feature reduction methods that are deliberately targeted to near-term quantum machine learning or just quantum machine learning in general, right? And then there also needs to be research on the other side about, okay, what are the kinds of quantum circuits that we should be even using as quantum feature maps?
Well, thank you so much, Travis.
Thank you.
I think we have reached the end of our 2 hours. So I would like to thank both Travis Scholten and Nick Bronn from IBM Quantum for giving this presentation for the Quantum Science Center Summer School.
It has been super, super wonderful. So thank you for having us.
Yeah, thank you, both of you. I hope you have a wonderful rest of your evening.
Thank you.
Thank you. Take care.